lecture in the Helsinki Distinguished Lecture Series on Future Information Technology. My name is Teemu and I am the host of the series, and I will introduce Andy Hopper, who's a professor at the University of Cambridge, and where he's also the head of the computer laboratory for now 12 years. Professor Hopper is a fellow of the Royal Society, fellow of the Royal Academy of Engineering, and he has a great track record in both academic and industry collaboration sense. And as the head of the computer laboratory, he has been taking part in dozens of different industry collaborations. Personally, he has been involved in over a dozen of startups, and he has been involved in the development of, for instance, the ARM architecture and the Raspberry Pi technology. He's been named, among other things, to be among the 100 leading practicing scientists and the 100 most influential Britons of the modern age. And so without much further ado, I will introduce Andrew Hopper and invite him to give us a lecture where he will tell us about how to use computers to ensure sustainability of the planet.
Right. Thank you very much. So no question, now you can give me questions. And you're all going to rush off and drink SEMA, right? That's what I've been observing. Have I got that right? So good luck. I will be joining you, and look forward to my cultural experience as much as possible. And tomorrow I'm going to Rovaniemi, just to do even more cultural experience up there, just to have a look. So what I'll talk about is what a computing person might think about computing in an aggressive way, not a defensive way, and its relationship to sustainability. Okay? So that's what this talk is about. So the title is supposed to mean something positive, something forward-looking, the way the world might be, rather than just saying sustainability or green or whatever. And I will say sustainability and green quite a lot, but I mean something a little bit beyond that. So when thinking about this, one can think of 4 categories. Anyway, that's my framework, and let me explain it to you. One can think of 4 categories of how computing relates to sustainability. And they're shown over here. On the left, we can talk about the actual digital infrastructure itself, and at some level that's got to be optimal in whatever parameter you want, but fit for purpose and optimal and not using in particular too much energy. Second category is that we can use that digital infrastructure to sense the planet and then optimize something physical to improve the use of resources, transportation for argument's sake. The next one is that as we do this more and more, we become much more dependent on the computing. So it's got to be much more reliable. And also we start predicting things, and automating things it becomes even more, in a sense, difficult. So how to do that? And then finally, how do we deal with the dilemma that we've got the developing countries where population is growing, and we are in no place to say they can't have a better standard of living, and yet their use of the physical resources will tend to increase. And so the last bit is what, if any, actually there are some things can be done in digital, particularly by those people, so that their standard of living can go up, and they don't have the footprint that we have, and we're in no position to tell them that they mustn't. So a little more colloquially, so that's my framework. I'll talk about each one of those things and give you examples of projects and activities and so on. But just to give it a slightly more colloquial set of labels, so you might call the optimal digital infrastructure green computing. The sense and optimize you might call the other way around, computing for green. So the first one is more efficient, the second one is use computing to make something green. The predict, react, automate, I'll concentrate on one aspect of it, which is this more reliable guaranteed computing. And the last one you might call green wealth creation. So let's start off with the first one, green computing. So, energy in computing systems is an important area which has figured for a long time. The total energy use of electricity in 2015 was about 20,000 terawatt hours, and it's hard to work it out, but the core data center and internet was about 2% of that, and the end user terminal devices were about 4% of that. And data center design has improved over the years considerably. A decade ago, the effectiveness of a data center in terms of energy efficiency was about 50% or 2 to 1. In other words, the energy used for computing as opposed to all the energy used for other things was about balanced. It's much improved now, and that ratio is about 1.15, about 15% is used on other things. So that's tremendous progress. So I won't talk too much about that, that's kind of done deal, take next. However, we may be at a time when energy proportionality is the important way to think of computer systems design for this green computing, this optimal digital infrastructure perspective. Just turn the screen so I can see something myself. So can we have the idea that we have proportionality of the use of energy in the CPU, in the processing, in the networking, and in the storage? And by proportionality, I mean, can we get to a situation where energy is only used if there is some useful purpose for it to be used, end purpose, rather than being either in a poor standby mode or even perhaps some kind of proactive wasteful computing which has no useful purpose, and we move to that. So the notion of energy proportional processing, networking, and storage is something I will now say a few words about. So energy proportional processing, in other words, data center design. Well, here is a slide which is from Google. It's a Google cluster slide which shows what proportion of the time do we have a particular utilization. So what it's showing on the left is utilization being mostly at around 30% at its peak, and on the right we have a much improved situation where across the cluster of 10,000 machines or whatever it is, it's moved to the right and we have much better utilization. And virtualization, the idea of being using Zen or one of these technologies, Zen came out of our department, but there are others. You can repack the data center and on the switch on the energy on the computers that are actually reasonably full. Reality is still that the efficiency is not that great in this sense. It's not that proportional. So 20, 30, 40%, I think this is optimistic on the right, but depending on the type of job, if you've got a batch job, if you can delay the job and batch it up with others, then the utilization can be 100%. So that's energy proportional computing aspiration, kind of getting there. Remember these systems, whether Google or the others, they can worldwide place data, place programs, rebalance in any basically way they like because of their business imperative, which is the service level agreement to the customer who's paying for the advertising. But actually energy is a cost which they can figure out. But the tool for doing this placing, moving things around at a huge scale is available. And in some sense, it's a done deal. I haven't got a slide for the networking, but I would say the networking situation, the switches and all that, are in a much worse situation. It's much less energy proportional, much less of that networking infrastructure gets opened up and shut down into standby modes, not least because there aren't the control interfaces which give you the detailed energy interface across which you can manage. Although those are coming along, they're our various largest projects to do that. Energy proportional storage. What do we make of this? So here is how Facebook actually do it, and so we actually have energy proportional storage to some extent. So here is the current Facebook situation. This is from them about 2 or 3 months ago. They have about 400 billion photos. So they have hot storage, warm storage, cold storage, and very cold storage architecture. So hot storage is where it's read a lot, and they have a replication across multiple data centers from a performance point of view, from a reliability point of view, and there's a 3.5 stretch factor. In other words, there are 3.5 copies in effect. We think copy in a very generalized way. Striking is interesting. For resilience and performance. So that's the hot bit, most performance. And the data cools, their data cools by about 500 in the first year. So the next level of this energy proportionality is warm storage, where you read it every now and then after this 500x, and they reduce that to a 2.5x stretch. And therefore, if you say counting energy, or the embedded energy, or the manufacturing energy of all that storage, you would have the 2.5 stretch, would be cheaper, and they migrate 1 month old data from the top one to the next one. Next one is cold storage in their systems, where they have an architecture of very cheap drives by the million, and they actually only power them up, the way the striking works, at 1/15th of the time only. And there's a 1.4x stretch in that part of the architecture, but the performance is, from a latency point of view, is rather less, because the data is read almost never, and they're shutting down the power on these drives, these millions and millions of drives that they actually have. And finally, we have very cold storage, which essentially would read never question mark. So Facebook say, we will keep your data forever. So I can understand that commercial point, but intellectually, what is forever? Anyway, optical storage, Blu-ray disc and that sort of stuff, seems to be an appropriate way to have this most efficient from every point of view, except performance, the storage. So I would claim that energy proportional storage also essentially exists. Here is one up-to-date example. So what can we do? Because it's all happening, right? So it's a done deal. Well, maybe we can do something along these lines. We'll use an energy that's renewable, and we'll execute computing tasks where renewable energy is available. That's a done deal as well. You've got one up north here, which is a done deal. So that's not. So maybe the next bullet, use renewable energy that cannot be used for another purpose. Well, we're getting into something that perhaps we can try and do. So we're trying to now use energy at some granularity of that energy coming up and down. Is it 100 milliseconds in a second? Is it a minute? Is it more relating to pumping water uphill, which is a way of storing energy? So the idea is that maybe we can have some benefit by using energy that can't be used for any other purpose. So how do we do this? How do we chase this energy around the globe? Do we replicate the programs? Well, that's not too difficult. Data sets, that might be a problem because they might be huge. And if you've got replication going on at scale, that's expensive against some footprint, some energy use. Do we do both and so on?
But that's an interesting area. I had a PhD student finish about 4 or 5 years ago on this very topic. So I think there is an angle, and the research question continues to be what proportion of the world's energy can be used for computing, in particular energy that would not be available to for any other purpose. And there can be two things. One, there just happens to be no load requirement at that moment for that energy, or even further, the energy source, the renewable energy source, is so far away that you could not get a cable back from it to transfer the energy, but you can still get a fiber optic cable and a communications fiber optic, whatever, out there and suck up all that energy, which you just can't use because it's too remote. And it's renewable energy. If it's oil, you can pump the oil. If it's gas, you can pump the gas. But if it's wind, this is a way of thinking. So I think this is an interesting line. I think 10 years from now, 15 years from now, 20 years from now, not today. And I think if the answer were, say, 15% of the world's energy used for computing, that would be an excellent answer. And then photonic networks are very interesting because they're more than energy proportional. A photonic cable, the further you go, the more energy you essentially don't use, right? So it's sort of, not quite, but it's reasonably independent of distance. So the notion of placing things in what today might seem extraordinary physical places, but which you can get to in the middle of the ocean, in the middle of Siberia, in the middle of Spitsbergen, whatever, where there is inherent renewable energy, is an interesting twist on this, because if you believe that those will develop and that capacity will be there, then this approach in particular will be very attractive. So finally, let me give you some thoughts. So, which are just technology trends, which might suggest that this is possible. We do have, as I've explained, on the server side, reasonable proportionality, not great. And on the terminal side, you can argue about it, but most of the mobile phone architectures and all that sort of stuff are intrinsically reasonably good from this point of view, in the sense that the energy they use is mainly by reasonable architectures and are not too bad from that point of view. Internet of Things is likely to be also reasonably energy efficient, in particular if it's one of these things which has to have a battery for a lifetime and you throw it away. By the way, if you want a research topic into electronics, I want biodegradable Internet of Things devices, because otherwise if you put it out, you'll have to find it back. That'll be very expensive. I just don't begin to understand how you're going to retrieve the Internet of Things infrastructure if you want it at scale, unless it's some version of biodegradable. Workload trends. I would argue that the workload trends for this approach, for this twist on sustainable computing, is in the right direction. So we're tending to deal with more and more data, and that data, big data, algorithms, indexing things, preparing things, finding patterns, Bayes theorem, neural network, take your pick, is quite a it's a computational task which is frequently not real time. So you're preparing stuff, and think of these as new style batch computations, and therefore they can be delayed. And so the workload trend for 10 or 20 years from now, I would argue, is for much more of that sort of stuff in the cloud. So that's good. So in summary for this bit, energy proportional computing, networking, and storage. Well, you tell me whether you agree with me that in some ways it exists. The research question, how much of the world's computing will use surplus energy? What might be the target? Is it a reasonable target? And then just as a reference, it is worth thinking, what might the architectures be like? So for the processing side, is it a latency-driven architecture? In other words, you place the work, the computing jobs, purely driven on the latency, in other words, speed of light. If there's a latency required to a human being, which is 50 milliseconds, then that defines how far away from the human being you can have anything. Or is there perhaps going to be some trade-off where it's actually going to be energy-driven, either energy in the sense we don't care, which is quite likely, or in the sense that actually there is a price and we'll pay a latency price, even though the performance is a little bit less good, by moving to some energy source which is further away. And finally, on this ultimate storage architecture, this is a little bit for the theoreticians, what is the footprint today of something we'll keep forever? Okay, so if you really think you're going to keep all data forever, tell you that I don't get it. So I would have thought you've got to throw away something at some stage, right? You can't keep everything forever. So anyway, you can discuss your thought, but I would have thought something like a digital notary. In other words, you agree kind of in every sense, a societal sense, and actually in a contractual sense, that you will compress the data, throw everything else away, and that's it. It's gone, and you just agree that data is gone. You can't keep everything forever, if you see what I mean. Okay, we'll move on. Number 2. Computing for green. Big Brother project, ultimate Big Brother project. So from a computer science point of view, we can think of building a sensor-based digital model of everything on the planet. And then we can Google everything on the planet, every living thing, every object, every changing thing. We can Google them in space-time. And we have some lovely computer science problems that traditional computer science problems that arise because these numbers just numerically tend to be quite big. The scalability is of a different order. The way you implement all that is interesting and is a traditional, very good, but traditional way of achieving new results. So how do we do it? Coverage, fidelity, scalability, performance, and what's the point? I'll come back to what's the point. Okay. But I was talking to a colleague earlier about trees, and there are 3 trillion trees on the planet, or thereabouts, according to the BBC. So that's 400 trees per person. So you could have you could be observing 400 trees, each one of loving them to death, maybe using some remote sensing, Internet of Things, you tell me, and you could love each tree to death. There will be 1 million drones produced this year. Maybe it'll be drone technology that does it. So that's slightly crazy, I know, but actually the crazy things happen. So if you had said 20 years ago we're going to be indexing everything on the internet in the way Google and others do, you'd have said, ooh, that's a bit crazy. Well, it happened. So let's have a look at something that relates a little more to energy, perhaps, optimizing energy. So infrared sensing is interesting. So the picture on the right shows an aerial view of a part of London where black is cool and red is hot, so it shows you the housing stock and the loss of energy through the housing stock. The picture on the left is a drive-by infrared image of a house, and there are companies like Assess, which do the picture on the left and the map bottom left, Assess, something like that, where basically they keep reasonably up-to-date infrared images of a city and make the information available. And of course, heat goes up through the roof. If you're losing heat through the roof and you fix it up, then you've used some technology in order to spot that and perhaps improve things. Why not have a live infrared picture of the whole world, just as a generic facility that's available, temperature map at fine grain of the world 10 or 20 years from now, that just tells you, it's just public information, you don't need any drive-bys, satellites, maybe in real time even, or discuss. It's doable. Maybe, I don't know, maybe the military are already doing it, but in my perspective, these sort of things are perfectly technologically attainable. Whether you want it or not, that's a separate issue, but I'll come back to that. But I've been a little bit fanciful, so let me give you a much more practical example to show you that I'm down to earth. So I'm the co-founder until recently chairman of a company called Ubisense. And this is one of these companies, it's 250 people, so it's not too small, and it's a public company now on the London Stock Exchange. It's one of these indoor location things, localization as it's called. But the way it's configured actually has an interesting perspective on sustainability. So the way this technology works is that it's actually bespoke, specialist. There is a tag. You put the right, you got the tag. You put the tag on an object, say a person. You've got some receivers, so it's got some. It's essentially a radar system. Okay, not RFID, it's radar. And so it's an active tag and receiver infrastructure with this sort of accuracy up to 15 centimeters, can be better 95% of the time with that sort of range. One of the major applications is in car manufacturing. 5% of the world's cars are now made using this technology, where you take a tool used in car fabrication, which has a reasonably high energy use. So this is not a little phone, which, this is at scale in the manufacturing industry, fastening devices. And what we have here is a production line of cars, BMW as it happens. There is the tool. The tool is tracked in real time. The car is tracked in real time. The tool is rigid, the car is rigid, so you know the relationship of the tip of the tool in real time to everything on the car. And so you can now control the tool, like switch it on and off. You can set it to the right parameter. This is a very reliable system. This is not a hint system. This works, right? One tracking mistake every 3 months across the production line. So you can automatically program the tool with the correct settings. So this is an example of sense, actually optimize, control, in the loop. It better work very well. And because it's in an industrial situation, the energy optimization of this production line, this is a mainstream car production line, is not in small quantities. They keep it as a trade secret exactly what it is. But these are big numbers, not little numbers, as a result of all this optimization. And by the way, it saves 15 seconds on each operation across everything that the production line does. And then there are further derivatives like how many tools you have, how you organize the production line, how you can go up and down to multiple operations because now it's automatic, how you can actually redesign the whole production line so the operator can do several things and the line isn't just a linear one. They all relate to use of resources, and then finally you know what everything's doing so you can tell how much energy you need if energy is your pleasure, because a tool that's away from an operation doesn't need to be provisioned with energy for. So you can now go with your tariff to the outside and say to your supplier, I don't need energy for the next 2 seconds, can you give me a discount? Or, can you take that into account? That's all fanciful stuff. That doesn't happen at the moment because this is a straightforward, very complex, large industrial application, but there it is. Another one of the same technology in use is across Airbus production lines, where again you're tracking, and the point I'm making here, this is sensing big things, which use lots of energy. It's not in the noise, and it has to work, and I'm pleased to say it exists. At the consumer end, the glittering prize, and I heard some stuff here, is to do the same thing but using just a default smartphone. And that's coming along very nicely, where you use all the sensor systems on a smartphone. This is my colleague Rob Hall in the group has done this, concentrates on it. You use all the sensors on a smartphone. You map out the top right picture is some kind of a map of, say, wireless coverage or light intensity or whatever. You've turned everything on, whatever it is that you're using to try and get the localization going. And it's also interesting, because it's a forward reference, but if you have an infrared, we don't at the moment really have infrared cameras on these smartphones. But if you did, and it's not too difficult technologically, in fact, in some sense, they have to get rid of the infrared sensing to give us a visual image. And we go into mixed mode imaging. Again, you get a temperature map and a visual map, and you can fuse them in different ways, which gives you sensing of the environment, which isn't just position, but is from a sustainability point of view, potentially even more powerful, because every farmer on the planet will have such a thing in due course. So we're collecting data, and let me just say a few words about data collection, because who owns the data and all that sort of stuff is an interesting question. So my colleagues Andy Rice and Alistair Beresford have a project called Device Analyzer, which essentially distributes a modified operating system, Android operating system, to users who wish to participate in an experiment which reports on the use of that mobile handset they have in terms of, well, more or less everything, okay? What does it do? What's the protocol? What are the apps? Everything, right? But how do you do properly so that you're beyond ethical, not just ethical? How do you set up a framework which enables people to participate in this. Well, here are the things we've gone through. There are 30,000 people participating in this or thereabouts. And here it is. First of all, there is a legal agreement with the University of Cambridge, right? So you can't do anything unless you agree to these principles, basically the chain letter, right? But it's the brand, the power of the University of Cambridge. And the University of Cambridge doesn't sue people, so it's you know, but there it is. There are two levels of ways data will be used. For generic data, which is a particular category, you know, basic things, once you've agreed to be, that will be shared. But if there are specific projects that are required by some user, potential user of this data, then a second level of permission for that project only has to be agreed and given. The application, this Android application, is never bundled with anything else. It's always visible. You have to do it. You get a reminder of what you've agreed to every month. You can always access your own data. And once you agreed, even the external data is only released after 3 months cooling off period. Okay? And then we only send metadata. So this has been successful, but actually that overhead of doing it in that way begins to give us an indication of what I don't want to criticize anybody else, but this is trying to do it in a way that we learn about how people might tango, right? How they might participate with sharing their data and how to make it so that they don't eventually either get really fed up with you or in some sense disappear. Okay, one more perspective. Okay, I'm slightly jumping around, but just bear with me. Here is another concept. So I had a PhD student finish this a few years ago. How do you, so you've got the data, ethically, you're doing all this sensing. How do you feed it back, and so what? So here is a concept which I think is very appropriate, which is that we develop and have available for everybody on the planet a personal energy meter. And that energy shows what energy you're using. But as the first bullet says, it has to be complete. So all energy is accounted for on the planet into these meters. You can't have gaps. So it has to be, all these fancy words, sensed, what you sense, embedded, how much energy did it cost to make the thing that you're using, the shared, how much of the defense, the military is allocated to you, because actually they all use energy, or the hospital system, or any shared infrastructure. Shared, and how much do we hypothecate? And it has to be accurate, bounded, personalized, so that I believe it, my actions relate to me. So what we have here is an illustration. This is not the truth. Some of it is the truth. Most of it is just an envisionment. It's not real. So, this may never work. Take it all with a pinch of salt. But it shows an app running on some smartphone, week of year, and then in these different colors, different types of energy that I've used, transport, hypothecated, health service, and whatever. How could we possibly construct such a thing? How could we use sensing, hypothecation, what you've done is allocated to me, machine learning to imply things, and so on and so forth, such that we have such a thing? I think it would be a very attractive thing. An example I gave somebody earlier is when I go on that train to Rovaniemi tomorrow, there'll be quite a big use of energy. And I'd like to know two things. I'd like the train to broadcast to me. What's the instantaneous electricity used, the pantograph, and how much energy? And then how many people are on the train? Not who they are, how many, so that I can divide my, so my allocation of that train trip, I will see, and I would like to know. And at the moment, I argue most people haven't got a clue what those numbers are. And the number between an empty train, difference between an empty train and a full train is humongously different. It's quite good news if it's full, but if I'm going to be, because everybody's been drinking their, what do you call it? their SEMA, and they're not getting on any train tomorrow morning, right? And I'm going to be the only one. I don't drink, as it happens. That number is going to be 2 megawatts as the train starts, right? So it's interesting. So again, we've done just the beginnings of this sort of stuff, and also the feedback. So there's information, but also the feedback of what you've allocated has to be of the right kind. Because if I can do an analogy, if you go to a restaurant and you immediately agree that you're going to share the bill equally, then if everybody gets the most expensive thing, your incentive isn't to stop that, right? However, if you have the right incentive scheme and therefore the allocation of some energy onto your meter, then that might have the positive feedback saying, okay, I've got, it's giving me a number which encourages me to do something appropriate. And so there are dilemmas all over the place here. There's privacy versus sustainability. So remember, this is computing for green, and we're sensing, and we've got all this data. There's privacy versus public good, sharing information about diseases or something. A very important one is privacy versus unexpected consequences, positive. If you had said Facebook will exist before Facebook, they would have said, you're mad. I did my first location system and paper in 1992, 25 years ago, okay? And I remember going to conferences, and this was locating people in buildings, right? And saying, you're here, and therefore routing calls and calling party identity. And I got to conferences and I got shot, especially in America. This is terrible. This is the worst thing ever. And now we can't live without location. We're sharing location. We're sending our identity. We're taking it. Everything's gone completely the other way. Same with Facebook. So just unexpected consequences. It's almost a definition of success, of impact, is to do the exact opposite of what the user wants. And then they say, privacy versus wealth creation was to do with business. And then who is Big Brother anyway? Because we tend to think of them as being Big Brother, but it's us because we're doing all the measurement. It's actually us that are the Big Brothers, I would argue. So here are some thoughts. I'm giving you some potential solutions. They're just my thoughts about the framework for the big data that the sensing optimizing requires. So the governance of big data. So the ownership, who is it? Is it the target? Is it the collector? Is it society? Well, a mixture of those. Trust. Do we trust government, companies, ourselves, or third parties? I would say that a little bit like with standards for telecommunications. I would hope that people like the IEEE start coming, well, maybe others, coming up with standards for the way data is used in particular situations, compliance standards, which then lead to trust and people are happy. Business, how does business work? Everybody at the moment thinks that they will own the data and therefore they'll make a huge amount of money. And it's the first time there's been a technology where everybody knows ahead of time that it's happening and everybody's already positioning. It's not like a faster network or something like that. It's completely different. So it'll take some time and it's not going to be instantly because these are big problems. But I think consortia will start forming where for business reasons multiple companies will agree to share data in particular ways and have appropriate tools. And then finally, society. I think it's important to consider societal data and agreement through either standards or legislation to share in a public way some of this data. So for example, the amount of oxygen or carbon dioxide in this room, we may declare, if measured, is a public number, not owned by the sensor or the company or the aggregator or whatever. Guaranteed computing. So this is, remember, now we've got computing in the loop and it better work. And so this is just one little flavor of, it's a big problem, reliable computing. Many people are working on it, but here is a little nuance on it, what I call guaranteed computing. By guaranteed, I mean if it doesn't work, you can do it again and it will work or it'll be replaced. So it's not perfect computing. It's not formally verified computing. Neither is it debugging. I mean, something that is in between, if you like. And I argue that we want it not just for sustainability, but just in general for managing of complex systems. And just another example is as machine learning improves and we use combinations of those sort of algorithms, which tend to be statistical, therefore guaranteeing performance across something that is statistical and intrinsically is an interesting research topic. And for this guaranteed computing in the bigger space of formal methods, better programming languages, better computer architectures and so on, we've got the kind of technical challenges I described. So here is the particular flavor. These are live projects. I'm going into some detail now, but these are projects which deal with provenance in guaranteed computing systems. So we've been working just on the provenance, which is a complete history of a piece of data and its transformations. So the idea is we keep a log of everything, right? Super log. And we can do this at various levels. And so if you know what's happened to data, if you find a bad bit of data, you know all the places it was used, so you can go backwards, correct, and forwards again all the places where that data was used. You could do that automatically, so this could be some kind of active computing. Or you could do it more like a garbage collector. Every now and then you'll say, well, here are the updated values. I want to go backwards to all the places where I've used them, and then automatically compute forwards, if you have this sort of provenance trail. But clearly there are problems to make this scale, to make this work properly, and so on. So, I've written some uses, validation, reproducibility, auditability, so on and so forth. Let me just give you one little connection to the previous thing, which is how do you deal with users who say, I don't want this application using this data, therefore you can't have my data. And it never happens. Well, here is a little angle using provenance. You can say, for the permission bit, please give us permission, but on a conditional way. We'll keep a track of everywhere it's used, and if you change your mind, we can undo it all, okay? So this would be an example of using this sort of provenance mechanism for big data. And you hope that the user says yes, and by the time there's any kind of decision to be made, there is enough, they've gone hook, line, and sinker for it in the same way that has happened frequently, and they never withdraw it, but they gave permission in the first place because they knew they had the technical mechanism to withdraw their permission, and they would trust you that all the places where the data was used would be identified and it would be deleted. This is a hierarchy of computing systems, hardware operating systems, library, applications, and the colored things are funny names, computer science names, as ever, for different projects we've got. So just bear with me, I'll just give you a little flavor. So MapReduce. What we've been able to do, my postdoc Sheriff, PhD student postdoc Sheriff Akush has been able to do, is for MapReduce to provide tags which keep a track of the mapping and reducing, of the hashing into buckets on the map step, and then aggregation on the reduce step. So that the blue is the conventional MapReduce, which frequently used for big data, and the red are the tags. And so now you can go backwards through the MapReduce as well as going forwards, okay? And the overhead isn't too bad. It says less than 10%. I don't know what it is, 20%, whatever it is, but it's not too bad, both in space and performance. And so you can go backwards in big data and verify that the data was right, do auditing, obviously, prevent leakage of sensitive data because you can keep track of things and so on. So that's one example of this guaranteed provenance. Another one is, since I'm in the home of Linus, really, we've been able to do it at the sort of operating system level, user level, where we keep a log of everything that happens, all calls between operating systems, processes, data, and so on. And this just runs in the background and is available as a property of the computer system. So that subsequently, if you have, say, an activity like this is a paper, you've written a paper, and the paper is made on this machine. The paper consists of some text, some tables, which were rooted in some experiments, so on and so forth. The way the paper came together is automatically in background mode made available to you if you so wish, so that the provenance of all those numbers and all that data is just a property of the computer system, and you just have to worry about the paper, not where it came from. And then if you pass it on to somebody else as a reference, you get the whole background stuff as well as the paper itself. So I hope I've, what else have I got on this one? Giving you just a little flavor. There's another level, since you do networking here, we also do the same thing for just straightforward network configuration. How did I end up with these 1,000 computers on these networks? What was the sequence of steps which had the following drivers, the following configuration applied to it? Here is the provenance of it. We keep a log of all that, so that's towards the hardware level, the same sort of thing. So I argue that provenance is just one interesting new property you can have in a computer system, which you couldn't have before, which will help with all this. And finally, green wealth creation. What about this developing world in particular, so-called developing world? What can I say about that, if you give me 5 minutes? So what is your answer? What will you do to make it so that those people can have a better standard of living? You're not going to say they can't have the footprint. So my argument is maybe, we can assume, I think reasonably, that they will all have a very nice phone, that they will have a service on that phone at reasonable price, and there won't be barriers on the internet so that the information flow will be there. They can access all information. And that may, and this is now the most woolly, the least quantitative part of what I'm saying. But in order just to get a flavor of what this might mean, let me again show you one little project that we've done, which is we went to Rwanda and we did a deal with the operator there where we collected all mobile traffic in Rwanda for a week. So first of all that data collection, we have to apply to this as well, right? So you can't have the data, sorry, unless you go through this old protocol, sorry, no can do. And there were about 13 terabytes of download, 1.25 terabytes of download, and all this sort of stuff. And so we're just trying to get a feel for how these networks work, and actually it's a bit of the green computing in mind. So here is a little interesting graph which just shows the week. Friday to Thursday was the week, so it's time along the bottom, days of the week. And megabits per second, and is the maximum download speed. And the red is a smartphone and the blue is a feature phone. And here is another thing which shows in that data the top handset brands by the number of bytes sent and by the users, by the number of users on the right. And so just going back to the previous one, well, you can see that more in smartphone, and the peaks are about 20 megabits per second. But here, all the most popular phones are crap, okay? And they're crap in two ways. They're not only out of date, they don't have firmware updates. So from a security point of view, this is a nightmare, right? So just the beginnings of an indication what they might be able to do to begin on this journey. And this is real data. This is not, in fact, I believe it's a unique data set which has its own problems. So nevertheless, I think it is a very important line. I think it is happening in a developing world. There are applications like you may not have heard of, you probably haven't heard of, like Mgadi. This is essentially Uber for rickshaws, right? And actually that person can make a little bit more money as a result of using, this digital thing. And payment is also important. And so fulfillment using electronic money is very good. Crowdsourcing work, Mechanical Turk. I'm not sure how much of a success the Amazon thing is, but that's a good thing from this point of view. And then Massive Online, of course, they have access to the information, so I think that's a broader, interesting component. So to finish off, let me summarize. I hope I've given you an idea of at least how to think about what's the crossover between computing and sustainability. I've said that in the energy field there is a traditional energy efficiency design component, and we can argue about whether it's any different to do it for green or not, but actually this twist on renewable energy is important. The computing for green is observing the world, but it's what you sense, how reliable it is, how you feed it back, and how do you handle the data. And I was thinking more of an ethical position rather than a societal position rather than a business position. I could give you the business one as well. I talked about we depend on this stuff, so what we're going to do about it, because basically if we believe that we'll embed computing in the sustainability of the planet, the current infrastructures, the way computing works is not good enough. We have to improve. And finally, I'm very happy that, at least in my travels, I see the development, the use of digital infrastructures in the developing world, and I can begin to see how they will not need to build so many roads or do so many things in the physical world in order to increase their standard of living, have smaller families, and therefore benefit the planet. Finally, here is a picture of my group doing well, I call it blue sky research, but as somebody pointed out, this is grey sky research, but there we go. So that's my research group, and obviously I've been reporting on there and many other people's work to you. Thank you very much.
Okay, so now we have time for some questions, and I would ask people to raise their hands, and I will bring this microphone to you, and you can ask your questions, and we'll all hear it.
Don't be shy.
I did warn Andrew that we are shy, so...
Otherwise I'll ask myself a question, and then you really think I'm weird, right?
In your personal energy consumption metering thing, you did not have food included. Would it make sense to include it as well?
Yeah. Well, conceptually, I'd love it because that crosses over into health and sort of stuff like that. So conceptually, yes. I've avoided the medical because that has got its own, in my projects, rather my perspective, because it's got its own ethical problems. So we've gone as far as sports, which includes a bit of food, but actually not in any substantive way. And this is more for the energy and sustainability point of view. But yeah, it would be great. I mean, the concept is everything, right? I mean, why not? And by the way, my own energy footprint is hopeless, right? I'm absolutely terrible, right? So I'm not, any kind of principled person from this point of view. Sorry. Does this fit into the Finnish situation? Do I gel? I said, let's count all the trees. A lot of trees in Finland. I said, energy in some sense is not as important as you might imagine, the green energy. Do you agree with that?
It's about the energy consumption. You touched upon already this, that we have the sun up there, and so not all energy usage is the same importance in a certain sense. And you spent not so much time on waste things and pollution, and wouldn't that be like more important to address all the plastics in the sea or whatever, and here you can have also computing involved in your second part about observing the environment and trying to optimize this kind of waste point of view.
Look, you're absolutely right? So the big problems aren't with energy with us. The leakage of methane, for example, from the Russian methane gas infrastructure distribution system is a huge problem. How to generate, nuclear versus, those are the big numbers, right? This is in the noise. So I completely agree with you in the sense that, there are efficiencies to be had, there are optimizations in the core system. So I'm just talking as a computing guy, and I'd be delighted if, in the same sense with the car manufacturing example, which essentially optimizes resources in a particular configuration where one company can buy the system and, it's all manageable in a sense. It would be very good to use technology to help with any of these other things. So, if we had a methane map of the world live, right? Not infrared. Now let's have methane. You can do methane sensing. You can do it remotely to some extent. You can do the Internet of Things in the world infrastructure, gas distribution infrastructure or production infrastructure with methane sensing, which is open source and crowdsourced. In other words, it's public information, right? That these places have to have these sensors, and they broadcast in the public, in the open. That would be great. That would make a difference to what people think about it all. Yeah.
So I'm curious, so to deal with inefficiency and waste and things like that, for example, you mentioned methane leakage. There will be presumably people, or when you said they don't have to build roads that they don't need, there will presumably be people who have vested interests in not making things super efficient. Somebody who has the contract to build that road that is not actually needed. So there will be people who don't want things to become more efficient and who will oppose publication of, they don't want all of this information to be public. How do you suggest to deal with resistance to this kind of thing?
Well, you're right again. Who am I to say? But here are little nuggets of information. In a sense, you need a big disaster and then something happens. So if you take the Volkswagen scandal, and actually everybody's doing it, okay? They're fiddling around. That may trigger a response which might be, I would wish it to be, and I have no idea whether it will, that they'll be much more open about that stuff because we will not buy cars so much from the suppliers who aren't. So if each, again, forgive me being a little optimistic and, who knows, but if each car were to broadcast, we only bought them, if each car were to broadcast the last 10 minutes worth of its emissions on the Bluetooth, and anybody nearby could say, or I'm getting in that taxi, I'm not, that would be the beginning of, and it's just possible because there was big trouble, right? So if I was, take a manufacturer like Class, the combine people, right? They have a policy that they will never own the data, they will publish, they're not in the data business at all, and they'll be completely open about it and so on. They're not trying to hoard it. So that's an interesting business perspective. I happen to be an advisor to the board of directors of one of the world's largest oil and gas companies, okay? And I have been for 5 years. I don't normally do this, but it's one of the world's largest, so I was interested. And everything I say about methane and so on just translated onto one of the biggest companies, and they're thinking through how to do this. This is a Western company, given the Paris Accord, because their shareholders are saying, what are you going to do? And his CEO is saying, what kind of things can we do? And people like me are saying, well, look, be a bit more public, because as it happens, your methane leakage is better than your competitors. Actually, if you do this, maybe we can have the digital push that information down and make some difference to your customers. And the filling station of the future, you should think through having some parameters which relate to that. But I'm relatively optimistic that these vested interests can be cut across by the amazing, because our technology is wonderful I would say it's wonderful in the sense that the distribution channel called the internet, or even some of the phones or whatever, is fantastic. It's one to everybody very quickly. And so if you do get your foot through the door, it can be absolutely wonderful. I mean, I've experienced this myself. It's not a green point, but I don't know if any of you use a technology called VNC, which is remote desktop, and that's one that's gone through the roof in terms of use, and it's just a few of us initially in Cambridge doing some open source stuff, and it's just bloody remarkable. 1 billion copies now. Where did that come from? Well, these 1 billion copies of the next thing are something that relates to information and influencing people about buying, that, Would you agree, or am I not making sense to you? Good. At least there's the beginning of an answer rather than being gloomy, if you see what I mean. And you're not and I'm not, so there we go.
Yeah, first of all, thank you very much. It ties from a different perspective, for example, issues like the internet of energy. Because, I'm looking beyond oil and gas, and if you look at things like, you have microgrids, where people, they have solar panels on the roofs. And by means of blockchain, neighbors sell it to each other and access energy. I think that's brilliant. But so I'm on the one hand very optimistic. On the other hand, I'm going to be a bit rambling and perhaps be a bit of a party pooper, because it's a forever balancing act. I have a legal perspective, so perhaps I'm at the risk of being really boring. Of course, there's the issue of the Paris Climate Agreement, and I think that's the way we're going to have to go. The rise of sea levels is so worrisome. It's far greater than people sometimes are aware. So I mean, we are going to have climate change refugees. So you know, but I just wanted to take issue because I read something today. So please forgive me if I'm sidetracking. Because and this is the forever balancing act.
Yeah. Go ahead.
You know, public goods. For example, in the New Scientist, I don't know if you managed to read, and this touches England. They, for example, it's there's just come out that Google, it has ambitions in healthcare. And it has an agreement, a data sharing agreement with NHS. That's the British Public Health Service. They want to do kidneys, kind of kidney diseases. And now it's come out public that they actually have access to all the patient data. So, despite the fact that they say that they're searching people's kidney disease to find out, big data. So actually, they have access to all the patient data. And that really worries me because even if that data is, stored in Europe, who's to say, because it's an American company, that another foreign company, government doesn't want to have the access. So I'm just saying that, data protection does apply, and I risk of being legally boring,
No.
I'm not sure every British person wants their health data, sensitive health data to go, from because of foreign companies. So just a reminder of that.
Yeah.
It's a forever balancing that.
Yeah, no, I agree. So basically, in Europe, we have a right, from a legal point of view, that we can withdraw, and in the US, you can't withdraw. It's just the way it's used, roughly speaking, if I've understood it correctly. So yes, there are issues and problems and real disaster scenarios in a bad sense. Agreed. However, that whole business that I went about, here is how we do device analyzer, here is a protocol that we've developed, here is the feedback loop. Those are interesting things, and I heard about another project that's happening here along those lines. The more the better, because that's the contribution I would suggest we can make. Try and understand some of this sort of space, and then my comments about societal data and different uses of data, the business uses and so on, and standards, all are, in a sense, I'm agreeing with you, and here is the beginning of an answer, but there's surely a disaster because the notion that because conceptually it seems a good idea, you will share medical data right across the patch, even though in some principle sense it seems, why it's not, why not? There might be some good that comes of it. Is a disaster waiting to happen? I agree.
I see the benefits of big data and so, but people cannot become just their data their data object that's harvested.
Yeah.
Okay.
But again, so big data. I gave you a map reduce traceable system, only 10% overhead. This works on big data. So if you want to control the flow of whether this data was used over here, I've got here is a technical tool in absolutely totally mainstream open source Hadoop computer science infrastructure. That's gobbledygook to you, but it's the mainstream one that everybody can pick up and use, whether they will or not. But at least technically, there it is. This data was used over there. Shouldn't have been. Bang. Anyway, I think, thank you so much.
Hi, thank you very much for a very interesting lecture. My question also concerns climate change, and I was wondering if you have any ideas or suggestions how ICT could contribute to climate change adaptation in developing countries, which you have mentioned already, but not limited to developing countries.
I'm sorry, I haven't really considered it from that point of view. So the only answers I can give you are very superficial and very simplistic, right? And I'll just imagine something which is fanciful. It's a story. It's not real, but just might be possible. So, food production, food security, food production. How can we improve that? Well, there might be a technological answer. So here is my dream scenario. Everybody, even the poorest person on the planet has a what we today call smartphone, an up-to-date thing, and they're either cheap enough or, like has happened with texting in East Africa or whatever, the way tariffs work, you're a loaned one or whatever, let's just assume that that's the case. May or may not be true. 2, the phone can measure, so it's got sensors, it's got in particular a high definition camera, but give me the temperature map as well. So it's got an infrared coating, or it can get rid of the coating on the camera that stops it measuring infrared. So now I can take a picture of a crop, both in terms of color, visual, and temperature. And it's located, so I know where it's taken because it's got a GPS. So now I'm going to take some pictures. I'm a farmer. I'm a farmer in Bangladesh. And I'm taking high-resolution pictures, which are localized, and I'm sending them up to a service, which is kind of going to help me be the agronomist. It's not just a pricing service, but it's going to analyze that. And going to send me back some information saying more nitrogen, slightly, if the leaves around the edges, there's a plant thing around the edges are showing signs of distress, that can be a little bit of water shortage. There are aphids, you can spot animals on it, so on and so forth. Obviously, you've got a temperature as well, either directly or just by location, you know what the temperature was. So now you can have feedback to the farmer saying, water it or whatever it is at a micro level, but for everybody on the planet. That's the big difference, right? It's not just an average person. Maybe in that there will be better efficiency of particular crop production, and therefore maybe it's not a direct answer, but the fact that the climate has changed, the technical means for, say, growing the food so you're not hungry, may be made easier. I'll stop at that, using that loop. At least that's the best answer as a computer engineer I can give you, because I'm not a nurse or a doctor, right? If I was a doctor, I'd say go and give a better toilet, right? But I speak as a computer engineer, and that's the best answer I can give.